Well, welcome back to the wonderful world of kinetics and the study of reaction rates. This video is going to focus on integrated rate law plots. So a diagram or a graph or a plot looking at concentration and time relationships to see can they predict the order of a reactant based upon that graph. And here again, we have our integrated rate law expressions. Again, we have zero order, first order, and second order reactions. We have our rate law, which is the relationship between rate and concentration. And then we have our integrated rate laws, which is the relationship of concentration and time. We notice that because our rate, again, is affected by our concentration in a certain way, whether zero, first, or second order, there's different ways that that concentration would change over time. And so first, what we want to talk about is what is a half-life and how that relates to the integrated rate laws and how that leads us to identify the half-life time with regard to zero, first, or second order reaction. So again, the half-life is the time it takes for the concentration of the reactant to decrease to half or 50%, the original concentration. And we notice there's three distinct expressions for that relationship between the time it takes to get to 50% and the order of the reaction. So for example, if we look at like a zero order half-life, so the T sub 1/2 is equal to the original concentration divided by 2 times K, because we know that in a zero order reaction, basically our rate is equal to K, the rate constant. So if we're decreasing by 1 molarity per minute, and we start with a concentration of 1 molarity, it's only going to take half a minute or 30 seconds to go from 1 molarity down to 0.5 molarity. So again, what we notice here is that a couple things to observe is that our half-life is dependent on the original concentration because our rate is independent of concentration. So if I start with a concentration of 0.5 or a concentration of 0.005 molarity, they would have the same rates. That's because it's zero order, it's independent of, the rate is independent of the concentration of the reactant. First order, what we'll notice is that our half-life is equal to the natural log of 2 divided by our rate constant. So again, our rate constant here is important because that helps us see how fast the reaction would be happening relative to maybe temperature and those other variables, and then we multiply it by the concentration of our reactant, A. And what we notice here is there is no concentration of A present in our expression. And what does that mean? That means that our rate decreases as we see our concentration decreasing, but because of the fact that it has this one-to-one decrease where the concentration decreases and at the same proportionality, the rate is decreasing, what we notice is there is no dependence on the original concentration of our reactant. And so if I'm going to go from 1 to 0.5 molarity, that's going to take the same amount of time for a first order reaction to go from 0.5 to 0.25. So for example, if I start with 1 molarity, and let's say our half-life is 20 seconds, what that means is after 20 seconds, the concentration of A, again, this is our original concentration, is going to be equal to 0.5. Well, after 40 seconds, or 2 half-lives, we will decrease from 1 to 0.5, and then we'll decrease another half of that, not half of our 1, but half of our 0.5, and the concentration of A will be equal to 0.25, or half times the number of half-lives that we have, times our original concentration. Now again, we can plug this into our rate law expression if we want, and our integrated rate laws, but here what we're just seeing is that because we've gone through 2 half-lives, we're going to go from basically 100% to 50%, then 50% to 25%, and a third half-life is going to go from 25% to 0.1 or 12.5%. So it continues to get cut in half, and the reason why that we observe that with our first order, not our zero order, is that again, this rate is independent of concentration for zero order, whereas our rate is dependent on concentration for our first order reaction. And then finally, we'd see here if we're looking at our second order reaction, we notice again, we are dependent on the original concentration. So whatever concentration we start with, that's going to affect how long it's going to take to go from a concentration of 1 down to 0.5 if we're looking at that as being our original concentration. So again, hopefully our half-lives tell us, what we notice is they tell us something about the relationship between our rate constant and our concentrations, but they also tell us something about how long it takes to get to half of the original concentration. So we notice each of these half-life expressions, they all have our K value. And then they also, depending on if it's zero and second order, they also include some concentration dependence. And so we see that our first order, because of the nature of the fact that we have a one-to-one rate to concentration dependence, that our half-life, or the time that it takes to go from 100% to 50%, is independent of what our original concentration is. So now that's kind of like an introduction, reminding us a little bit about our half-lives. Now what we're going to do is we're going to take these graphical representations, or these representations of concentration and time, and we're going to look at what kind of information can we get from a graph or a plot of concentration and time being our two variables. What we're going to do is we're going to think about these three possibilities. So we want to investigate what kind of information can a concentration versus time data graph give us about our rate law or integrated rate law relationship, basically the kinetics of the reaction. So we're going to look at different possible plots for A going to B. This is just a basic, very generic reaction. So if our reaction is zero order, that would mean rate is equal to K times A to the 0th power, or just K. So our rate constant is our reaction rate because there's no dependence on the concentration for the rate. That's what the definition of zero order reaction would be. We also know that the concentration of A at some time, this is our integrated rate law expression, is equal to the concentration of A initially minus K times T. And so we think, what are some variables that would be constant and what would be even variables that would be changing when we're looking at our time dependence on concentration, how those two variables relate to each other. So what we see here, our initial concentration is a constant for a specific experiment. So is our rate constant for a specific experiment. So if I start with 5 molarity at 25 degrees Celsius of reactant A, those two variables are constant. The two variables that are going to change would be our T value, our time, and then the concentration at that time. So if I were to graph the data that I would have for time, so time would be our independent variable. Our dependent variable thing that's going to depend on the time, that would be our concentration. If we were to plot something like this, it would look, maybe depending on how fast or how slow our reaction is, something like that. And again, we would see that our slope is equal to change in concentration over change in time, which is also, in this case, our rate, which if we go back up here to our rate law expression, we would see here as negative K. The reason why I would say it's the negative of the rate, because we're thinking here that we're decreasing concentration for our reactant, and our reactant is a negative value, and we correspond that back maybe mathematically, thinking about our rate law expressions and our reaction and coefficients, and that's something that we've done previously. So if we were to graph our concentration of A versus time, it's going to be something that's linear. Now, where did we get this idea that our slope is equal to K? Let's go ahead and rearrange maybe this equation here, our integrated rate law. So I'm going to keep it as our concentration at some time equals, and I'm just going to move negative KT and switch where our original concentrations were. So again, we said that our A is a constant, what we'll see is that that's actually our y-intercept. Our T is X, and our concentration after some time is Y. And so that would mean if we were to have a linear graph, we get Y equals mx plus b. So what does that mean for a zero order reaction? Our slope here is K, or negative K, and our y-intercept is equal to our original concentration. So see, there's a linear relationship between concentration and time when we're looking at a zero order. So kind of one of the major conclusions here, a zero order reaction, what we'll see is a concentration versus time plot is linear. And one of the important things that we can get from that is that our slope is equal to negative of our rate constant. Okay, we could also see that our y-intercept is equal to our original concentration here. And so we could say that right there, our y-intercept is our original concentration, and again, our slope is equal to negative K. So we could actually, if we plotted this, we could actually receive some good information about the kinetics of our reaction. In this case, the rate law expression rate constant. So that's a zero order reaction. Again, there's no dependence on rate. The rate is constant. So now let's look at the possibility. What happens if this is first order? So again, first order would be rate equals K times the concentration of A to the first order, or first power. So again, reminding us that our rate is dependent on the concentration of our reactant. So if our concentration decreases, our rate also decreases. If we were to plot, maybe we think, let's do the same thing that we just did with our zero order. So we're going to plot concentration of A, time, and what we notice is if we were to fill in these data points, we would see that there's actually not this linear relationship that we would observe between concentration and time. And again, we remind ourselves that our slope, in this case, is equal to the change in concentration of A over change in time, which is the opposite of our reaction rate. Well, we just said our rate is dependent on concentration. So as the concentration of A decreases, so does our rate, which is why we observe that our slope becomes more shallow, and more shallow as our reaction continues to go on. Our slope decreases, and so does our rate decrease over time. So we see here is that our slope is less steep, and that is because our rate decreases as our reaction proceeds. Well, this doesn't really give us any good information about our rate constant. And so we say, well, what information do we know that actually has maybe something that would be linear with regards to our concentration of our reactant and time? So if we go back to our rate law expression and our integrated rate law. So again, we have our rate law. Rate is K, concentration of A. We want to figure out, is there a way for us to identify our rate constant? And what we also know is that the natural log of the concentration of A at some time equals the natural log of the concentration of A originally minus KT. So again, we have our K value in here, time, and then we again go back to, let's investigate what are our constants and what are our variables that are changing. So again, our K value and our original concentration, those are constants for a specific experiment. Because they're constant for a specific experiment, the only thing that's going to be variable is our concentration and time. So those are the two variables that will change as our reaction proceeds. So then we would think, well, what's going to be something that is going to give us a linear plot? Again, let's go ahead and rearrange this. Natural log of concentration at some time equals negative kt plus natural log of a at some time. Again, what we're doing is we're putting our variables that are changing kind of next to each other. We just rearranged our natural log of a, original concentration, and k and t. We rearranged those a little bit. And if we said, well, let's plot on our y-axis natural log of concentration and our x-axis t. Well, that would mean that we should get something linear where we would observe that our slope, again, is equal to negative k, and our y-intercept, in this case, is equal to the natural log of our original concentration. So again, if we chose to manipulate or utilize our data in a certain way where we get a linear graph, because this relationship would be linear, if we graph this, again, we make natural log of a at some time, and then again time. We're now going to go from this kind of curved slope down to this linear slope. And this linear slope that we'd observe, or this linear graph, excuse me, because of the way that our rate changes over time with regards to our concentration, our slope is actually going to be equal to the opposite of our k value. So again, now this gives us the ability to identify what our k value is based upon the information that we know if we were to plot this in a certain way. Give us something that's linear. Linear graphs are easy for us to investigate and pull information out. It's easy to get the slope of a reaction, and our y-intercept is going to be equal to the natural log of our original concentration. So we see a couple concluding observations that we can make when we're dealing with a first order reaction. The plot of natural log of the concentration of A versus time is linear, and that's because of the integrated rate law expressions that we observed. And when we do that, our slope is equal to the opposite of our k value, and our y-intercept is equal to the natural log of our original concentration. So again, we notice that we're just choosing simply to change what our y-axis is that we're graphing, and we are able to extract some useful information there. So now we've done 0 and first order. If we go to, well, what happens if it's a second order reaction? What would the concentration of A versus the time graph look like? Again, this is where rate equals K concentration of A squared. So this is thinking of our reactant concentration is going to affect our rate squared. So the more our concentration decreases, the more our rate is affected. So if we were to graph starting off again with just concentration of A versus time, what we would notice is that this rate is actually going to change much faster, okay? So our slope, again, is equal to change in concentration of A, our y-axis, over change in time, which is equal to the opposite of our rate. So what we notice is that our slope is changing over time, and that is because of the fact that our rate is dependent on the concentration of A squared. So this is actually going to be more changing over time. Our rate is going to change more over time because of the fact that our rate is more dependent on concentration than a first order reaction. So now we've identified, well, that's not going to tell us anything per se useful. But again, if we go back to, well, what do we know about our integrated rate law expressions? And if we look at a second order reaction, we know that the inverse concentration of A at some time equals the inverse concentration of A initially plus KT. Now again, if we rearrange this just a little bit, we continue it with our concentration of A at some time. We're going to put KT and then the inverse of our concentration of A initially. And again, we think about, well, what are our constants? What variables will not change? Those two variables will be constant for a specific experiment, again, with initial concentration and a specific temperature we're looking at. However, again, we look and see our T and our concentration at some time. Those are going to vary as our reaction proceeds. Now, why is that helpful? Why is that useful? Let's go ahead and rewrite this again. So our concentration at some time equals KT plus our original concentration. Again, if we choose wisely what we want to graph, then we're going to have the ability to maybe get something linear out of it. So again, if we make our y 1 over the concentration, we make our x t, what we'll see here is that what that's going to do is that's going to make our slope equal to our k value and our y-intercept equal to the inverse of our original concentration. So again, now if we chose to plot this with 1 over our concentration and time, what we'll notice is that our slope actually flips here. And again, this is because we're looking at inverse concentration. So as the concentration of A decreases, what that means is the inverse of that concentration is going to increase, right? If you go from 1 to 0.5, that means your inverse concentration is going to go from 1 to 2 because it's 1 over 0.5. So that's why it makes sense that our concentration, inverse concentration, is increasing over time. And what we notice here is that our slope is equal to our k value and our y-intercept is equal to 1 over our original concentration. So now we have the ability to extract some useful information here when we're dealing with a second order reaction. So again, to conclude here with our second order reaction, a plot of inverse concentration versus time, again, y and x is going to be linear. And as that's linear, our slope is equal to our k value and our y-intercept is equal to the inverse of our original concentration. So now if we were to collect some experimental data and we were to graph them, maybe with these three possibilities, 0, which would be concentration versus time, first order natural log concentration versus time, second order inverse concentration versus time, maybe one of those is going to be more linear than another, and then that will tell us what the actual order of the reaction would be. So now that we have this kind of foundational information, let's work through an example together. Okay, so here's our example. We are given the concentration versus time data for this reaction. So 2A going to B. And from this information, just this table here, we want to determine the order of A in our reaction. So is it 0, first, or second order? And then we want to write out the rate law expression, including the value of K. So thinking how we can actually identify what the K value is. And then we want to calculate the concentration of A after 225 seconds of reactions, because we notice we only have data to 100 seconds. And so now we're going to put all these three pieces together in identifying some information from just experimental data. So now what we need to do is we need to figure out, well, we need to have three possible plots. Again, concentration of A versus time, which would be a 0 order plot if that is linear. Okay, so if our reaction is 0 order, that would tell us that this plot would be linear. Okay, so what information do we have that's going to give us the ability to identify that? Well, if we look at our R-squared, our R-squared tells us how linear this best fit line, how well this best fit line fits our data. And we notice it doesn't really fit it very well. We also look at it and we can kind of see that it starts above it, goes below it, kind of curves back, and then curves back around. So we notice it doesn't look very linear. And so because it's not very linear, we observe that for a couple ways. Just simply by looking at our R-squared value, we can also look at our just kind of observationally looking at the graph that we have there. That would probably tell us that this is not 0 order. Okay, again, we graphed it, we looked at this, and we observed that it doesn't give us a linear graph for the data that what it would look like. This would be a constant slope. Our slope would not change because our rate would not change if it was 0 order. Okay, so we say, okay, well, it's not 0 order. Then let's look at our other two possible plots. Again, we would plug this in maybe Excel and create some graphs. And so we would have natural log concentration versus time. That would be if it was first order, and then inverse concentration versus time, which would be if it was second order. And we want to think, okay, which of these two actually match our data a little bit better? We looked at, this looks pretty linear. This looks pretty good. It fits our data pretty good. Whereas this one, we notice again, we kind of have this weird curvature that doesn't really match our linear graph, our best fit line for this graph. We can also look at our R-squared values. The closer to 1 we are, the better it matches our data, the less we deviate from that best fit line. And we notice that our second order is not very close to an R-squared value of 1, whereas because this is probably pseudo data, not exactly perfect data, maybe somebody made it up, our R-squared value is really close to 1. And so we notice here, because of that, we can make the conclusion that this reaction is first order with respect to A. And the reason why we can make that conclusion is because the natural log concentration of A versus time plot is linear. And that's because it fits within the relationship that we would observe, the integrated rate law that we would observe for a first order reaction. Okay, so now we're able to conclude, that was our first question, what is the order with respect to A? It is first order. So that would be question 1. Question 2 wants us to actually write out our rate law expression. So that again is rate equals K times concentration of A to some order. That would be our general rate law expression. Because of the data that we actually have here, we have the ability to identify what our actual rate law expression is. We know that this is first order. We know our M value is 1. Actually, I'm going to change this because we use M already. So I'm just going to call that N. So our N value is 1. And then we also need to know, well, what is our K value? Do we know the rate constant? And we go back up to our graph, and we see here that our slope is equal to negative 0.0112. And we think, well, what are the units of this? This is change in y over change in x. Our y is just natural log of A, which is unitless. So that would be nothing. I'm just going to put a 1 there because there is no units. And our x is time. And so that would tell us that this is actually units of inverse seconds. And that's our slope. We know that our slope is equal to the opposite of k for a first order plot of natural log of A versus time. So that means we know now our k value is positive 0.0112. And I'm just going to rewrite that as inverse seconds, how we usually see it. So now we have our k value. Let's go ahead and write out our full rate law expression now at this temperature, 0.0112 inverse seconds times the concentration of A, again, to the first order. We all identified that simply from these couple plots that we have with our data. Now, finally, what we want to do is answer the question, what is the concentration of A after 225 seconds? Well, again, now we're looking at concentration of a reactant versus time. So again, we're thinking about concentration versus time. That means we want to use our integrated rate law expression. And again, reminding us we have two forms for a first order reaction. I'm going to use the other one. So the concentration of A at some time equals the concentration of A initially, e to the negative KT. And reminding us there is 4 variables here. We got to know 3 out of the 4 to find the other one. Well, we know our original concentration was 1 molarity. Okay, now how do we know that? Let's scroll up for a second. At time equals 0, we had a concentration of 1 molarity. So we know that's our original concentration. We know that our K value is 0.0112 inverse seconds. And we know our time is 225 seconds. So now we can go ahead and just plug that in. So our concentration after 225 seconds is our original concentration, 1 molarity. And then we have our e to the negative 0.0112 inverse seconds, 225 seconds. And then we go ahead and plug that into our calculator, and we get a concentration after 225 seconds, 0.0805 molarity. And so that's after 225 seconds. And so now we see that we have to kind of put all this information together, integrated rate laws, how that relates to these graphs or experimental data that we could use, and then we connected it back to maybe calculating our concentration after a certain time, or also looking at our rate law expressions.